So subatomic particles. All atoms are composed of the same subatomic particles. Protons, neutrons, and electrons. These are not the only subatomic particles. There are lots of other ones. But these are the three that matter to us in general chemistry. There's muons and gluons and Higgs bosons and all kinds of other crazy things that the physicists really get into. We're concerned with these three subatomic particles. So protons and neutrons have nearly identical mass. For our purposes, they're the same. 1.67262 times 10 minus 27 kilograms, 1.67493. Big deal, right? There's a small difference, but for the most part, we really don't care. Those are essentially the same. The mass of an electron, 9.1 times 10 to the minus 31 kilograms. So this is significantly smaller, roughly 2,000 times smaller. So if the electron was a grain of rice, then the proton would have the mass of a baseball. So protons and neutrons are very massive compared to the electrons. So as we see from these masses, 10 to the minus 27, 10 to the minus 31 kilograms, kilogram is not a great unit for expressing the mass of subatomic particles. Even something like a picogram is still not going to be the right size. So we invented a unit. It's called the atomic mass unit. That sounds a little flip. Oh, we just made up a unit. Where did any unit come from? Somebody made it up, right? So, yeah, that's not so strange. An atomic mass unit, abbreviated AMU, not an AMU, would be some relative of an emu. It's just AMU. Has a strange definition. One atomic mass unit is 1/12 the mass of a carbon atom containing 6 protons and 6 neutrons. So this carbon atom has 6 plus 6, 12 of these large particles. And we're saying that one atomic mass unit is 1/12 the mass. So basically, an atomic mass unit is the mass of a proton or a neutron. The charges of these particles are different. And so this table summarizes some useful things. Proton, neutron, electron. Their relative charges. Here are their charges measured in coulombs, and that's needed sometimes, but most of the time we just need the relative charges. The proton is a positive 1 charge, the electron is a negative 1 charge, and the neutron is 0. It's neutral. And then their masses. So here we have 1.00727. Well, we could just call that 1. And the neutron, 1. And the electron, 0. So for most purposes, we can think of the electron as really not having any mass at all. Which reminds me of this great T-shirt I want to get one. It says, "Electrons have mass." I didn't know they were Catholic. Ooh, I got a laugh. Yes. So electrons do have mass, but because it's so small, it just doesn't matter, right? So if you're walking through the woods and a leaf falls on your shoulder, does that add to the mass of the backpack you're carrying? Well, yeah. Is it significant? No, it's just one little leaf. You wouldn't even notice. And that's the mass of these electrons. They're just on top of everything else. They're so small they don't matter. So highlighted there, those are the things that you should know. You should know the names of the 3 subatomic particles, their relative masses, and their relative charges.